Okay, so we have looked at a number of examples of functions which are multi-value, right? Many of these came about when we tried to find inverses of functions which were single value. Right? So whenever you have several inputs basically take you to the same output, it's not a one-to-one function, and if you try to invert such a function, then you will be in a scenario where the same value of z will point to multiple different values for the inverse function. So let's take a closer look at such multi-valued functions in this lecture and see how to deal with this multi-valuedness. Okay, so so examples of multi-valued functions and how they appear, when we look at inverses of, say, functions like z squared, right? If you try to invert z squared, then you have z to the half, and so we know that both plus z to the half and minus z to the half when squared will give you z squared. So there are two different possible answers for any given z. And likewise, if you look at e to the z, we have seen that log of z is, in fact, there are infinitely many values of log of z, right? So that we can associate with log of z, right? In the sense that if you take the exponential of all of these different numbers, you'll get back the same e to the z. And similarly with z to the n in general, where n is some integer. So if you try to invert this, so you have the z to the 1 over n, right? And we have seen that the nth roots of unity, there are n of these, right? So in general, z to the 1 over n, there are going to be n different values which correspond to z to the 1 over n. And likewise, also sine inverse of z, we have seen, is connected to the log function, and since the log function itself is multi-valued, sine inverse of z is also multi-valued, and well, also the square root multi-valuedness also appears there, right? So technically speaking, you cannot really call these as functions, because the technical definition of a function is that given an input, there should be a unique output, otherwise it's not a function. But it is accepted parlance to just call these as multi-valued functions and come up with a practical way to deal with such functions. So one might think that you think of all these different possible values of these functions as representing separate functions, right? That could be an idea, and so that is connected to the idea of a branch, right? So you think of different branches, right? So instead of having just one complex plane, you think of it being made up of what are called Riemann sheets, and so then you might think that this is going to solve the problem. So suppose you are looking at something like z to the half plus z to the half could be one function, and minus z to the half could be a separate function, right? We could try to solve this problem by looking at them as two different functions, or which usually described as two separate branches. But this itself does not quite completely solve the issue, as we will see, because there are certain topological aspects as well which we should keep track of. So let's define a branch. A branch of a multi-valued function f of z it's a single valued function. Inside a branch, a function becomes single valued f of z, like we have already done it with the log function. So small log of z is multi-valued, but we looked at capital log. So, and it's in addition to it being single valued, we would also like it to be analytic, right? So it's a very important property that we want to retain. So we don't want to assign unique values to capital F of z, but in some arbitrary way. If you do this, then you're not going to keep the analyticity of f of z, right? So like suppose I'm looking at z to the half, right? I can have either plus z to the half or minus z to the half. Both of these are valid outputs, but I cannot assign plus and minus in some arbitrary way, right? So you should stick to all of them being minus or all of them being plus when I'm looking at neighborhood of a point as well counts when we're interested in the idea of analyticity, right? So we would like to make this function single valued, but also analytic in as large a region as possible, right? So that's why it's a subtle aspect, right? How to treat multi-value functions, right? So we must ensure that f of z behaves in a nice way in a neighborhood around the point of interest, not just at that point. Okay, so let's look at an example. Suppose, yeah, so this example will illustrate how it's not enough to just consider separate branches. It does not quite solve the problem. The reason is the following, right? So let's look at a simple example. So we'll consider the function f of z is equal to argument of z, right? We have seen that argument function is multi-valued. So given you may be at a certain point z, but there are, either you can represent it with a certain angle theta, or theta plus 2 pi is an equally valid angle to represent that point in polar coordinates, right? So this function, so what happens if you start from a certain point, you assign certain value, and then you slightly move around, you go around a closed path. Now the question is, does the function, when you come back to the same point, is there a way, even if you're in a certain branch, will you return to where you started, right? So if you ask this question, so let's try to work this out for f of z and consider two different kinds of loops, right? So let's say, okay, let's look at, so this is the complex plane, and then let's say I start with a certain point. Let me use a different color for this. Suppose I take this a path where I start with from a certain point and then I go up. So when I'm here, I assign the value theta equal to 0, right? So, and then I start moving up, slowly it increases, it keeps on increasing, and then I reach a certain point where, right, I'm supposed to measure the angle with respect to the origin, right? So if I were to draw a straight line from here, you can imagine a straight line from the origin all the way to, let's say this point, and the angle that this line makes with the x-axis would be the angle at this point, and then it keeps decreasing. As you come down, you see that it keeps decreasing, and then when I come back to this point, when I hit the x-axis again, it's going to be 0 again, right? It started from 0, it increased to some positive value, high positive value, which could be this angle, I don't know, maybe something like 30 degrees, 40 degrees, whatever in this case, and then it comes back down to 0. And then if I go around, and then if I come back to this point, that's the type of path that I'm thinking of, right? So then I go, so now it's in the negative direction, it goes back in the negative direction, and then I come back to where it's started, and then it has come back to 0, right? So it seems like there is no issue. But on the other hand, suppose I do the same kind of an exercise, but for a different closed path. So let me use a different color here. So this is path B. So suppose I start at this point, and then I start moving up. So the angle increases, and then I cross the imaginary axis and then come around. So you see that the angle at this point is actually pi, right? So I have not restricted argument of z to have only certain values at this point. I'm looking at the function small arg of z. So if I continue to go beyond this point, so it's going to increase. My angles will be pi plus something, so on, and then at this point it's going to be 3 pi by 2, and then I come back to this point. By the time I hit back this point, it has come to 2 pi. Okay, so what we find is, if I take this second kind of a path, I start from this point on the x-axis and then return to it in a closed loop, and then when I come back to where I started, the value I ascribe to the function arg of z, I'm at the same point, has changed by 2 pi. And if I were to do one more loop like this, suppose I go around, and then if I do one more loop, then now the angle is going to be 4 pi, and if I do one more loop, it's going to be 6 pi, and so on, right? So it's as if although you started in a certain branch, right? If you go around, you have to have a way to certain kinds of loops. You have to ensure that you have actually entered a different branch, right? So it's not enough to be able to think of a multivalued function as being made up of several different functions which all operate in different branches, but they have to be connected in this kind of a special way, right? So that's what makes this multivalued functions subtle, right? So we observe that whenever the origin lies inside such a loop, then you're going to get a different value for such a loop from the value that the function has at the starting point and the value that the function will take at the end point are going to be different. But on the other hand, if the origin were to lie outside the loop, then we saw an example where there was no issue, right? So in some sense, you're all part of the same branch. If you're if you're not, your loop does not include the origin, right? So we must be able to use a tool by which we can separate out these two kinds of paths. And so it's not enough to introduce the notion of a branch, but we also need to introduce something called a branch cut. So we must put a restriction that your angle theta naught must lie inside some set of angles which goes from theta naught to theta naught plus 2 pi. You have the freedom to fix your theta naught, but we must remove a whole array of array of points, right? So this corresponds to removing this radial line theta equal to theta naught from the domain of definition of the multi-valued function. So this is one way to solve this problem. So another way is to use something called a Riemann sheet, which let's not go there at this point. So let's think of a single branch and how we can introduce a branch cut, and then we can maintain analyticity of multi-valued functions in the entire branch except for that one line, or except for this cut, right? So if you make this restriction, then argument of z becomes a single valued continuous function of z, and at all the remaining points in the complex plane it's actually analytic, right? So this set of points such that such as this array which is removed to make it a well-defined and meaningful single valued function is called a branch cut. So it should be a set of points. Now a branch point is any point that is common to all the branch cuts, right? So we could have you have many sort of a stack of different branches in some sense, but they are all connected at this point and along the branch cut, in fact, right? So that's the picture that one uses when thinks of something called a Riemann surface. But at this point, let's concentrate on just a single branch and the presence of this thing called branch cut, and practically we can do all our we can go ahead and study analyticity and you do all the nice things that analytic functions have, as long as we don't cross this branch cut. So let's look at a few examples. So suppose we write r is z equal to r times e to the I theta. So the logarithmic function is multi-valued in an extreme sort of way, because it has for any given z there are actually infinitely many values that this function can take. So log of z is equal to log r plus I times theta, plus you have this freedom to add I times 2 pi m, where m can be any integer, right? If you choose a particular value of m, then that would correspond to one branch. So it has actually infinitely many branches, and if you choose any particular m, right, when you're dealing with log z and in a certain branch, then it's analytic within that branch as long as you don't cross the cut. So, and one special branch that we typically deal with is the so-called principal branch, right, which we've already looked at, and so that's defined with a capital L. So log of z is equal to ln r plus I theta, where you put m equal to 0, and then you have logarithm of any complex number in this principal branch is simply given by the Napier-Perian logarithm of the radius, that is mod of z plus I theta, right? So theta is restricted to lie between minus pi and plus pi. So here, in fact, we are making use of the capital ARG. The argument is also restricted to lie between minus pi and plus pi. So in fact, we have introduced a branch cut here along the negative real axis starting from the origin, which is actually a branch point, right? So branch point is the point where all these different branch cuts, they all interact. It's common to all the branch cuts, right? So in some sense, so you have to, if you take all these different branches, you have to sort of stick them all together onto this branch, and they all meet at this branch point in the Riemann surface picture. Okay, so let's look at another example. Similarly, one can define, suppose we looked at the square root function. So square root function has these two different branches, right? Either of these values would be equally good candidates. You could either take plus r to the half times e to the I theta by 2 with r greater than or equal to 0, or you could take minus r to the half e to the I theta by 2 with r greater than or equal to 0. So here, of course, r equal to 0 is a logarithmic singularity, right? So in the earlier example, so it's not defined at that point, the log function. Whereas here there is no problem. So a branch point could be a benign one, like here in this case, square root of z also has a branch point at the point r equal to 0, but it is just 0, right? So there are different forms that a branch point may appear in. So in this case, there are just two branches, so plus branch and a minus branch if you wish. And so in fact, you could do this kind of an exercise where we did it for the argument function. So if you take the positive branch and then go around in a loop around the origin, if you were to cross the branch cut, then you would actually end up in the next branch. So that's why even for to ensure that you stay within the same branch, you must impose this branch cut. And if you're taking any closed loops are not allowed to cross this branch cut, and then you remain within the same branch. So in this case, I have already restricted theta to lie between minus pi and plus pi. So again, taking argument to lie between minus pi and plus pi, right? So theta equal to pi itself is not included. So either of these would be an acceptable branch. And then, so in general, the nth root of a complex number has n branches, as we have seen, right? So we could write these n branches in terms of the n roots of unity. So we have 1 omega squared all the way up to omega to the n minus 1 are the nth roots of unity. So we could define z to the 1 over n. There are these n different branches. The value that your function would take if you're sitting in each of these different branches is given, right? So in some sense, what we are doing is we are converting a multi-valued function into many different single-valued functions and introducing the idea of a branch cut, so that you not only have single-valuedness but also analyticity in as larger regions. So if you stick to one particular branch and you don't cross the branch cut, then your function is very nice and well behaved, single valued, analytic, all the nice things are available for you, right? So again, the origin is a branch point here, and we have chosen the negative real axis. So we said that in general you can choose the branch cut to be any ray starting from the origin going to infinity along any direction, right? As long as you stick consistently to your branch cut, it doesn't matter. You can do your calculations in whatever the branch cut is. And the convention that we are following here is to take this branch cut to lie along the negative real axis starting from the origin. So let's look at another example. So if you have f of z is equal to z to the c, where c is some complex number. So in general, if you have z to the 1 over n has n different branches, so you will also have n different branches if you consider z to the 1 over n to the power some integer, right? So that would be of the form z to the power of a rational number. So what appears in the numerator doesn't really matter. So it's the denominator. So 1 over n or some other integer, capital M over n. So z to the capital M divided by capital N, where m is some other integer and n is another integer. This function also will have n branches. Now, but on the other hand, if you look at a function like f of z is equal to z to the c, where c is a complex number, right? If you don't, it's neither an integer nor a, the ratio of two integers, then this function is going to be, definitely it is multivalued, but in fact it has infinitely many branches, because you have to define this in terms of the log function, and the log function has infinitely many values, right? So we have seen that z to the c is defined as e to the c times log of z, and if we stick to the principal branch, then you can define this f of z to be just r to the c. R is a real number to the c, so there's no problem with that, right? So that is understood in terms of the Euler formula, and then you have e to the I c theta. So the whole point here is that we are restricting this angle to lie between minus pi and plus pi, and once again the branch cut is taken to be along the negative real axis, and the origin is a branch point. Now when you introduce a branch cut, so the function is not going to be analytic along the branch cut, and in fact there is a sharp discontinuity across the branch cut, right? So let's look at how this plays out, and this is called the discontinuity across the branch cut, right? So every branch of a multivalued function necessarily has this discontinuity across the branch cut. Yeah, so I mean the reason this happens is, in some sense, all of these different branches are glued together along this branch cut. It's somewhat hard to imagine, but you can think of like a stack of different branches, but they're all they share this branch cut, and you're not allowed to cross it, right? If you want to stick to the same branch. But actually what happens is, if you do cross it, you enter some other branch. So that's the picture of a Riemann surface. Each of these sheets, they're called Riemann sheets, and then you go around once. If you cross the branch point in one direction, you enter a different branch, and there is a way to do the bookkeeping for this. But suppose we stick to a single branch, right? And then if you cross the branch within the same sheet, then you have a discontinuity. But if you were to enter a different, the suitable one, then if you enter the right branch, then it's not going to be discontinuous. So that's the picture of the Riemann surface, which we will not look at this point. Suppose we stick to a single branch, and then you try to make if you cross this branch. So this is what some function. Let's look at an example where this discontinuity is something we explicitly work out. So we go back to the argument function. Let's say you stick to the principal branch. So we define f of z with a capital A. So arg is capital Arg of z, and then whose values we restrict to lie between minus pi and plus pi. Right? Theta equal to pi itself is the branch cut. And so suppose you consider some point which is sort of infinitesimally away from the branch cut, slightly to the positive side, and then there's another point which is slightly below the negative real axis. So we consider these 2 points. Za is equal to x plus I epsilon, and Zb is equal to x minus I epsilon, and we look at the case where x is less than 0. Then we have argument of Za, slightly above this point is going to be pi minus some delta of epsilon, right? So there is an angle associated with this small epsilon that you have moved up, right? You can compute it, but it's not important what the precise value is. It's just that some small value which is you have to subtract, so it's slightly less than pi, and on the other hand the angle which corresponds to the point Zb is minus pi plus delta of epsilon. So if you were to compute this limit, in the limit of epsilon becoming very tiny, what is the difference between the functional value slightly above the branch cut and minus slightly below the branch cut, then you see that it's, in this case, f of x plus I epsilon minus f of x minus I epsilon is just given by pi minus delta of epsilon minus pi. So this delta will anyway go to 0 as you take the limit epsilon going to 0. It's only this 2 pi that will remain. So there is this discontinuity 2 pi no matter where you are. So it's independent of how far away from the origin you are for this particular function, but it's a constant discontinuity of 2 pi. Let's look at another example. Suppose we consider the function log of z, right, which is our favorite multivalued function. And now, once again, if we do the same kind of an exercise, so we restrict the polar angle to lie between minus pi and plus pi. Branch cut, once again, is along the negative real axis, starting from the origin and going all the way up to minus infinity. And we consider these 2 points. ZA is slightly above the negative axis, ZB slightly below, and then we have to compute the value of the function slightly above and slightly below. So argument of ZA and ZB, as we've already seen, are pi minus delta and minus pi plus delta. So in this case, the discontinuity we can work out is given by f of x plus I epsilon minus f of x minus I epsilon will be log of x plus I epsilon minus log of x minus I epsilon. So we have seen that the way to compute this quantity is to just find the the Naperian logarithm of the mod of x, which is just a regular logarithm value of a positive real number, plus I pi minus I delta, because that's the angle, that's the argument of this quantity, which is just pi minus delta. So you have to do I times pi minus delta. And then, but on the negative side, you have minus log of mod x is the same, but now you have minus pi plus delta, right? So plus I times minus pi plus delta. So these two will cancel. So it is a pi minus delta minus I times yeah, so this is correct, minus I pi plus I delta. So in any case, the delta part is going to go to 0. As epsilon goes to 0, delta also will go to 0. Log mod x and log mod x will cancel, and then you're just left with I pi plus I pi, which is 2 pi I. So once again, we see that even for the log function, the discontinuity across the branch cut is independent of how far away you are from the branch point. Okay, so let's look at another example. So square root of z. Right? For the principal branch, we have square root of z. We can take it to be the positive value. So r to the half times e to the I theta by 2, and r is greater than or equal to 0. Minus pi lies theta lies between minus pi and plus pi. And once again, we consider za to be slightly above the negative real axis, zb to be slightly below, and then the arguments of these 2 points we have already worked out, pi minus delta and minus pi plus delta. So if we compute the difference in the value of this function at these 2 points, so we see that one of them is square root of x plus I epsilon, and the other one is square root of x minus epsilon. And so the way to compute it is according to this formula, right? So, and just simply using the value of the angle at these 2 points. So mod of x to the half times e to the I pi minus delta by 2. Then we have a minus mod of x to the half times e to the I minus pi plus delta, the whole thing by 2. If we combine this carefully, so we will see that the answer is just so it's the mod x to the half comes out, and then we have a cosine well, I mean, we can simply put delta equal to 0. So we have e to the I pi by 2 minus e to the minus I pi by 2, so which is nothing but 2i sine pi by 2, which is just 2i, right? So this is a is something that you can check, right? So we have looked at a few simple examples, but you can consider some other more complicated, if you wish, multivalued function and try to compute the discontinuity across the branch cut. So once again, I emphasize that this discontinuity appears if you stick to the same branch, right? So in some sense, what you should do is, if you have the complex plane, and if you have made this your forbidden region, in some sense, you have chosen this entire region is your branch cut. So if you are going to look at the properties of your function, as long as you move around like this, and then it's not a problem, right? Anywhere here, your function has all these nice properties, it's analytic and all this. It's only here that you're not allowed to cross, right? So we will return to this at a later time, but at this point, since we have looked at so many multivalued functions, it is useful to complete this discussion about how to deal with multivalued functions and how to make them single valued effectively inside a single valued branch, as it is called, right? So, and the principal branch being a special single valued branch. Okay, so that's all for this lecture. Thank you.